you. The next presentation is by Filippo Trevisi from Politecnico di Milano.
Yes. Hi everyone, I'm Filippo from Politecnico di Milano. I'm presenting today my PhD thesis, which is named Conceptual Design of Windplanes. Windplanes is just a kind of catchy name I found for flight gen airborne wind energy system, but all the methods and more or less apply also to ground gen fixed wing. And my thesis is structured in two parts. The first part addresses the fundamental research question, given a wingspan, which design maximize power, and the second, if wind planes can fly stable orbits. So let's go to the first research question by addressing a similar research question we went through in conventional wind. So in conventional wind, we asked, given a blade span, which design maximize power, which in mathematical terms is a maximization problem, in which we have the power at the denominator, which is function of the design, and at the denominator, we have the reference wind power passing through a reference area. And we know that conventionally, we take the reference area as the swept area of the wind turbine, and this is letting us to ask this question: which one of the three turbines should we pick? The one on the top with really high solidity, the one on the bottom with low solidity. We all know that is something in between. And this fundamental question led us to scale up wind turbines and go to bigger size. Let's again go to a similar question to my fundamental research question, which is, given a wing area, which design maximize power? And this mathematical term is again a maximization problem of power at the denominator, which is function of the design, divided by the wind power, passing through a reference area. If we pick this reference area equal to the wing area, then we pose this question. And then we ask which one of the three planes should we pick? And we somehow can understand that the one on the bottom with really high aspect ratio has low induced drag, so we probably is the one we will pick. And this fundamental question has led us to really high aspect ratio planes as in the literature. So now let's go to the fundamental question of my PhD. So given a wingspan, which design maximize power? Again, a maximization problem, power, numerator, denominator, wind power passing through a reference area. Now we want to pick this reference area function just to the wingspan. So we take a disk with radius equal to the wingspan as a reference area. And now we can ask which one of the three planes should we pick. And you can imagine that the one on the top has really bad aerodynamics. The one on the bottom doesn't have much area, so we pick something in between with a finite aspect ratio. OK, those are somehow preliminary considerations that now let's put some math and modeling. We start with a really simple model, a 1 degree of freedom model in the tangential equation of motion. So we assume circular trajectory, and we model indeed the plane as a point mass. And we take also a vortex model for the aerodynamic induction. So we have a model to compute the induction at the plane. If we use this model, then the tangential equation of motion is the one up on the top right. We can do a step further in the characterization of this equation of motion by multiplying it with the tangential velocity to get to a power balance equation. And now with this power balance equation, we can just normalize it with the reference power we just defined to get to a power coefficient version of this equation. And this coefficient version of the tangential power equation is led to the definition of the CP and CT for those systems, power coefficient and CT and thrust coefficient. The power coefficient is function of the power coefficient on the onboard turbines and also their non-dimensional radius. And the lambda, which is the wing speed ratio, so how fast is flying, the plane is flying compared to the wing speed. If we do the integral of this expression over the loop, over the trajectory, then we have just a balance between the electrical power and the aerodynamic power, which is actually what we want to look for, this balance. OK, with this model, we can formulate some optimization problem. The first is an optimal control problem, in which we modify some control variables for some given independent variables. And we use an harmonic balance methods to look for periodic solutions. So we look for periodic and solution of this 1 degree of freedom system. We can modify, again, this to get to an optimal design problem by including among the design variables also three design variables, which are related to the aspect ratio, the tether diameter sizing, and also the non-dimensional mass. Among the control variables, we have the CL and how much we load the onboard wind turbines. I'm going really fast, but I want just to show you the results and bring you home the key messages. So with this design problem, then we can actually look at the results. And we start by analyzing three optimization problems. The first is a purely aerodynamic problem where we set gravity equal to 0, so we look for steady solution. And in the first problem here on the top right, we see that among the design variables for the design problem, we just have the aspect ratio and the tether diameter, so we don't have the non-dimensional mass. Then we include gravity in the second and the third problem. In the second problem, we still don't have mass, so we keep the mass fixed. And the last problem, we include the non-dimensional mass among the design variables. So the first thing we can look is looking at the aspect ratio of those systems. So we see that the optimal aspect ratio by fixing the wingspan is an aspect ratio which is finite and has a low value for all the systems. Then we'll see the mass, the non-dimensional mass. In the last optimization problem, this non-dimensional mass is actually finite again. So it's telling us that we have a finite mass. And we'll see this a bit in a while, why we have this. But conceptually, let's keep in mind that the mass is the parameter determining the trajectory radius. So if you have a large mass, we'll have a large trajectory radius. A small mass will mean a small trajectory radius. Then the last thing we can see is the operating CL. So the operating CL is telling us at which operating point we fly our plane. And the operating CL is the CL at which the airfoils maximize the CL over CD, which is the point of maximum efficiency of the airfoil. And if we do a sensitivity analysis of running optimal control problems, we have the figure here on the right, in which we show that the CP, or the power, is maximized at this CL. What does it mean? Let's do a step back. If we pose the fundamental question I'm posing in this thesis, then it's the first question I'm asking here. So given a wingspan, which design maximize power, which means maximizing the CP as I'm defining in this thesis. And then this led us to finite aspect ratio. And again, to use airfoils which maximize the metric CL over CD. And that's a good news because we know how to build those airfoils. They are used in many applications, wind turbines among those. Let's go to the second question, the one asked in literature. Given a wing area, which design maximize power, which is maximizing the power harvesting factor as it is defined in the literature. This is leading to very high aspect ratio, and also to airfoils which maximize the metric CL cube over CD square, which unfortunately is leading to airfoils we don't know how to build. So a lot of efforts went into designing those airfoils. So we see how this fundamental research question is leading to really different design. Again, showing some of the results, we see that the wing speed ratio, so how much the plane velocity is over the loop, fluctuate due to gravity. That's also a result. And we see also, if you look at the CP as function of the wind speed on top right, we see that the plane performs bad at low wind speed, the heavy plane. And that's something that we expect. We are some power losses due to gravity. And on the bottom right, we see that we run this sensitivity on the optimal mass, finding that there is an optimal mass. Why there is an optimal mass? As we said, because if we fly really tight loops, then we stop too much the wind. We create a lot of induction. If we fly really large loops, then there is a lot of potential energy fluctuating over the loop, and then there is an efficiency associated to that. So now it's time to take some conclusion on this first part of my thesis. So we defined this CP informing about the power per unit wingspan. And we saw that this led to a plane with finite aspect ratio and the need for airfoils which maximize CL over CD as other application in aeronautics and wind energy. Then since large loops penalize the CP because of the potential energy exchange, and small loops penalize the CP because of the dynamic induction, we found that there is an optimal finite mass. So now the question is actually how can we build these planes? Which material should we use? And what will be the structural design? So time to go to the second fundamental question on my PhD thesis, which is about stability. 1 minute.
We don't have so much time.
I'll run, but I jump to the conclusions. I like to start with this quotation from Akani Power, in which they state that they don't really understand the stability. So how can we assess stability for planes, for wind planes? We have a periodic nonlinear solution, so we should use Floquet theory or similar methods. But why don't we just take out gravity, find an axial symmetric solution, and study the agent analysis of the LTI, the linear time invariant system, about this steady solution? That's what I did. But first also, I needed also to look at the nonlinear trajectories. So to do this, I had to have a nonlinear simulator with a rigid body equation of motions, in which is a fully nonlinear simulator, okay, with an aerodynamic linearized about nonlinear operating points. The aerodynamics is nonlinear. And again, we look for periodic solution with an harmonic balance method. That was implemented in T-Glide, tetragliding system design, my optimization framework. And yeah, that's a bit the framework, but I'll jump to the conclusions. So the control strategy I used was basically an open loop in which I trim the horizontal stabilizer, the elevator, and the turbine induction to constant values over the loop. I actuate cyclically the ailerons, and I control the rudder in closed loop. Why the rudder in closed loop? Because of stability. So if you look at the LTI, then you can see if the plant is stable or not. And the agent analysis I'm showing here is the open loop, in which we have some modes that are really close to the imaginary axis, means that they are almost unstable. So the closed loop is actually to damp those modes. Here we have an animation of the pendulum mode, which is, if you design properly the plane, that is stable, and that's mainly by means of the dihedral angle. And then we have this precession mode, which is not influenced by aerodynamics in open loop, and we see that because the degree of freedom entering this mode are yaw angle and the one related to the trajectory somehow, and not really the other 8 degree of freedom that are entering the aerodynamics. So we needed feedback to damp this mode out, basically. Okay, just jump to the conclusion on this second part. We solved this nonlinear equation of motion, the rigid body problem with an harmonic balance with this aerodynamic model linearized about nonlinear operating points. If we take out gravity, then we have a steady axial symmetric solution. We can formulate an LTI, and we can look at the solution of this problem. And we find that the plane should be trimmed in the circular crosswind trajectory, which maximizes the projected area. We want to capture as much wind as possible. And the vertical stabilizer push outwards. And then we find that the pendulum mode is sensitive to the dihedral, and the precession needs feedback control to increase the stability. And then if we include gravity, we have periodic solutions. And then we propose this simple control strategy, which is to trim the elevator and the turbine induction, and to actuate cyclically the ailerons to redirect lift to stay airborne, and control the rudder in closed loop. And we found that there is a moderate reduction in power due to gravity with the design I'm proposing. So those are the references I used for this presentation, and you can find more information on in my PhD thesis is available online.
Thank you.
Thank you.
I think you had 1 hour for this original talk, right?
Yeah, yes.
More.
We discussed for 2 hours
Okay.
with the examiner, so shrink it down to 12 minutes was difficult.
Well, you spoke very fast. Are there any questions? Here, let me.
Thank you for your talk. I have a more general question about the CP.
Yes.
Because we also had some discussions within our company about what the CP actually means, because, I mean, for wind turbines, it's quite obvious. You have the ratio between the power you extract versus the power you actually have in the flow, but for airborne wind, this is not that simple. So I was just wondering if you have any suggestions how you would explain, let's say, somebody who doesn't know anything about airborne wind, what the CP actually means in that regard, or if
Yes.
if it's like a, can you also express the CP for airborne wind as an efficiency?
Yes, so I think DCP is great for design optimization. So when we need to design, and this indeed it comes after this fundamental question, so the need of defining DCP. When we need to, we're thinking about efficiencies, also maybe aerodynamic efficiency, how much we harvest from the flow, then probably there is some more other non-dimensional quantities we need to look at. It's a bit different from conventional wind, in which that's the rotor area, we express everything up based on that rotor area, and that works fine. Here probably we'll need different non-dimensional quantities to investigate different problems. So I'm not sure DCP makes sense for soft kites, and there are different metrics it's something we need really to think deeply. In terms of aerodynamic efficiency of how much we harvest from the flow, one could also normalize with the swept area, right? That could be something more similar to conventional wind when we think about limiting embeds type.
Yeah, I think we did this internally at SkySeals, and we either come up with a CP value larger than 1 or much, much smaller than 1. So it's not really satisfying.
I think this somehow tell you also like a direct comparison eventually with a conventional wind turbine with the same lifting body span, DCP, because you could build a conventional turbine with the same lifting body span, and then you know that the limit for that turbine is the Betz limit, right? So we are not physically exceeding the Betz limit, it's just a way around, but yeah, that's also give information about the design.
All right, thanks.
Thank you. I think we thank you again, Filippo.
Welcome.